Yeah, so let's go for it. Hi everyone, welcome to NYU Abu Dhabi Center for Space Science. Today's speaker is Doug Ming. He's a planetary scientist at NASA's Johnson Space Center in Houston. He's at the Astromaterials Research and Exploration Science Division. He has extensive experience in soil chemistry, mineralogy. He has numerous publications on the analysis of data from Mars's robotic missions. He's currently a science team member and co-investigator of MSL, which is the Curiosity mission rover on Mars. He was previously a science team member on the Mars exploration rovers, the highly successful Spirit and Opportunity rovers. He was also a co-investigator on the 2007 Mars Phoenix Scout and science team member of the 98 Mars Polar Render missions. So Doug, welcome, and it's all yours now.
Fantastic. Thank you, Dimitra, and thank you for giving this opportunity to come here and present my favorite subject, and that is the current state of sedimentary deposits on Mars through the eyes of rovers and landers. First of all, before I get started, I just want to congratulate you all on the successful insertion of the Mars Hope orbiter. Being having a real interest in the climatary evolution of Mars. I'm wishing all the success in your instruments, and I'll be looking forward to seeing data flowing down to good old planet Earth on the climate evolution and the particularly the higher atmospheric measurements that you're all going to be looking at. Okay, so to get started, I just want to first of all let you all know that we've done a lot of work on Mars, as you've all known, that if you follow the Mars program here in the US. The Mars exploration rovers, as Dimitra just was talking about, were highly successful back in 2004, and we lost opportunity just a little over a couple of years ago after an incredible longevity on the red planet. Then the Mars Phoenix Scout was highly successful in its search for water and some of the conditions at the polar regions of Mars. And of course, right now, the major beast I'll talk about is this Curiosity rover, which is a beast. It's incredibly large. It's about 1,000-kilogram rover on the surface. And of course, those of you that are following Mars robotic missions will know we had the successful landing of the Perseverance rover, and Perseverance is just getting started on its science. So I won't be talking about any data coming back from Perseverance today, except a little bit about the landing site. So first of all, in order to select sedimentary deposits on Mars that we would like to land with an asset such as a rover, we use a whole suite of cameras, the cameras that of course are on the orbiters. And we look for features that we think are likely to be sedimentary in nature. There are definitely layered material on Mars. We know that. The question is, are they done by, these layers put down by water? Are they put down by wind? Are they put down by explosive volcanic eruptions on the planet? We land one place or the other on Mars. And I'll just, like I mentioned, real briefly talk about the landing site of the Perseverance rover. We landed in Jezreel Crater last month, and this is a really interesting site. From orbit, you look at it, and can you see my cursor moving around here at all?
Yeah, we can see it.
Yeah. Okay, great. You see this feature here that kind of fans out over the bottom of Jezreel Crater. You can see it in this upper image really well. And our hypothesis is that this is some type of a deltaic deposit that was deposited by this large river that was flowing into this basin. So at one time, we think that Jezreel Crater was a lake with this delta deposit beginning to rove across the surface and will make its way over to this particular feature here, the delta. But we also from orbit have the ability to look at some of the mineralogical compositions of the surface through different spectral regions, and really the UV or the visible near infrared region are the ones we primarily use to look at spectral features for hydrated phases, such as carbonates, smectites. And we see these distributed throughout this fan. So this is why we're landing at Jezreel Crater. We think this is a place where water was very active. And this would be a place, if we were going to go to search for potential, say, biosignatures or anything that might suggest at one time that this area was habitable and could have supported life. With give you a little bit of information about spirit and opportunity and some of the sedimentary deposits we've seen here. I've been, as Nimitra said, very fortunate in my career that I have been actively involved in the operations, the design of these rovers and these various landers on the surface. And of course, the funnest part is doing science. But a whole lot of details about the rover itself. But again, from orbit, this is of the blue is low, so this is low here in the center of this crater. Red's high. These are more of the high materials. And the reason for this basin, so this water and sediments. So when we landed in Spirit, we were expecting to see sedimentary deposits. Here's the first views from the landing site in Gusev Crater. And I love that night. All night we'd been awake for a lot of hours and we were really tired. So we called this Sleepy Hollow. I think we all wanted to go to bed and get some sleep that night. But you can see the bounce marks here from the airbags that landed Spirit. What we saw, though, was a whole bunch of basalt. You see all these rocks out here. So instead of seeing a whole wonderful stratigraphic sequence of sedimentary materials, we saw a lot of litter of rocks that have been reworked mainly by impact and wind, somewhat of a basalt graveyard. And of course, if you're an igneous petrologist, this is really a heaven. But we saw these hills off to the southeast of the landing site, and we headed that way to examine those materials. Now, on the way over there, we did a lot of work on chemistry. Being a soil chemist, mineralogist, we were able to get a lot of great data sets that has now been used to basically describe the surface materials on the surface of Mars. They're basaltic in origin, which has not been reworked by the incredible tectonic processes here on planet Earth. So you do not see the reworking of these basaltic materials into more hard crystalline materials like you would in metamorphic deposits or metamorphic rocks. So the main thing is it's basaltic, but the main difference in the surface materials are these additions here that have been added to the basaltic composition. And the entire surface of Mars, gases and outgassing from this basaltic episodes, probably about 3 billion years ago, maybe to 2 billion years ago. And the chlorine and the sulfur have been added to the surface materials, and also a lot of nickel. And the nickel is primarily from meteorites that are bombarding the surface of Mars and working the nickel from iron nickel meteorites principally into the surface. One thing I will stress, since I'm a soil chemist, I love this, particularly from the standpoint of potential habitability. Way deep, but you see some very dark materials. At the top, it's redder, a little more coarser. At the bottom, it was very fine material of this trench. And when you look at the chemistry and other materials that are in this, you see some trends that are really striking to me. From the surface materials, you see down here in the bottom of this diagram, to the materials at the bottom of the trench, this purplish pinkish line, and you'll see that there's more Fe3. There's what we call nanophase iron oxides. This is the Fe3 component, but it's very, very small, and we see a whole lot more magnesium sulfate. To me, what this is indicating is that we have had water on the surface of this crater, and the water has percolated down through more soluble and smaller particles at the bottom. You're looking for something like this if it was wet enough, long enough. The question is, how long was it wet? And of course, you look at this now and you probably say not very long because it is awful dry. We made it to the Columbia Hills that I showed in the past slides. And we did this incredible trek across the Columbia Hills down to an area called Home Plate. But we went by some materials that were very high in sulfur. We went by some materials that were very high in silica. And then we saw some really interesting volcanoclastic sediments that I'll show real briefly next. So we called this a salt lick. In the United States, salt lick is something that we term as a place that a cow will go lick the salt. And so here we found this almost pure salt, so some kind of a ferric sulfide. So this was probably caused by the solutions or fluids, maybe sulfuric acid in nature, that were moving through these materials and precipitating as these things evaporated at the surface. Then we came across this beautiful layered material, probably one of the few layered materials we saw in Gusev Crater. And you see these layered materials that are draped over the topography. And our hypothesis here is that these were ejected from some kind of a volcanic activity. These volcanoclastic sediments then draped over the topography. And when we got over here and looked at this, we found something really interesting. And that these materials had a whole bunch of carbonate in it. About 30% of this material was carbonate. And carbonate, of course, is something that forms generally here on planet Earth. But of course, CO2 being dissolved in the solutions to precipitate the carbonates. They were primary iron magnesium carbonates. So this was pretty sediments. We had water. There were carbonates involved in this, meaning that they were probably pretty low temperature, not really high. And that these materials might, and the pHs are pretty alkaline, of course. For carbonates, you expect pHs above 7 for their formation. So here we have something that would be, in my view, potentially a habitable environment. But probably the materials in Gusev Crater that got the most attention of astrobiologists around these near Home Plate. On the top is another one of these salt licks, I'll call them. This is high silica. But we saw these high silica materials here that looks like they may have formed by fluids percolating up from the subsurface. And these we have hypothesized may be very like those types of high silica centers that form with hydrothermal activity. And this particular material here was one of the final candidate landing sites for the Perseverance rover. It didn't make it, but astrobiologists recognized that, hey, if you're going to go to Mars and look for potential of life, one place you go on Earth are these hydrothermal areas where there are lots of potential hydrothermal activity. And then this is the Home Plate that we encountered. This is probably the volcanic source for a lot of the activity that we've seen here in this area of Gusev Crater. And here is what I think is really interesting. On planet Earth, you see these big old chunks of basalt thrown out of these eruptions, and these things are underwater. They're the materials that when these bombs hit these, they cause these what we call bomb sags. And here is the example of this on the sediments around this volcanic center here in home plate area of Gusev Crater. So we think this was also caused as a ejection from the volcano. And I'll just stop and make sure, voice check. Is everything okay? Can you hear me still?
We can hear you with some interruptions. It's not always continuous.
Yeah,
But it's okay.
I'm seeing it's
But we are able to gather what you're saying.
is it really bad or?
No, it's not very bad, but I don't know how to avoid it.
Okay, great. I've been seeing the interruptions and I just want to make sure.
Yeah, there are interruptions, yeah.
Okay, well, okay, so now I'm going to jump across the planet, all the way to the other side of the planet for where the Opportunity rover landed. This was in a place called Murrius Mudstone. This is at a really unique area. This is more near the dichotomy of Mars, where we see the red is high again. This is the highlands area of Mars, and the blue is low. And these are the areas that have been suggested as potentially being ancient oceans on Mars. So Opportunity was the golden child of all spacecraft. Opportunity flew 300 million miles through space, and it landed in this crater. And I would call that a 300 million mile interplanetary hole-in-one. So it's incredible that this spacecraft flew that far and then ended up in a crater. And these were the images of that crater. We called it Gale Crater. And you can see for the first time ever from another planetary surface, we saw what material. So these were our first views from Opportunity. Not only did it land in a crater, it sees the first signs of a bedrock sedimentary material from another planetary surface. This signature from orbit that suggested that this area contained the iron oxide hematite. And hematite on Earth almost exclusively forms by aqueous processes. So our hypothesis here that this one at one time was an area that had a lot of water interacting with these basaltic materials, this hematite. Now, we did get down on the surface and land and look at these things, and we were greeted with probably the most spectacular sight of any spacecraft to this date as far as the surface of Mars goes, and that were these little ball bearings, or blueberries we called them. So we got to affectionately call these the Hematite Blueberries. And I won't go into a lot of detail about the chemistry, except to say that this was predominantly sulfur-rich, and it had a whole lot of iron. And when we used the Mossbar spectrometer, which gives you information about the coordination of iron, and therefore you can apply some information about the mineralogy, that it could only be the mineral jarosite. So jarosite is really interesting because jarosite only forms under extremely acidic conditions. This thermodynamic stability diagram I'm just showing just to show you where jarosite would reside on the pH diagram, and you can see it's below pH 3. So these materials in Murrius Mudstone have been extensively altered by sulfuric acid solutions, in my view, although there's a lot of competing hypotheses on how this might form. And one of those is that it could have formed like we see here on Earth for these lignite deposits, where we bring them to the surface, we expose those materials, and pyrite, an iron sulfide that is in these materials, then oxidizes, creating acidity and sulfates. So that is one of the hypotheses. Well, boy, that would be a whole lot of pyrite here. I'm more of the inclination that sulfuric acid solutions were prevalent in this area and help alter this material to form the jarosite. And then another way is to potentially have the sulfuric acid distributed across the planet by acid fog. And then there's also been recently a theory that solution subsurface went through a lot of basalt, dissolved iron, brought it to the surface where it was rapidly oxidized. But I have problems with this one as well, this hypothesis, because it's hard to explain the acidity when you're going through basaltic materials that generally causes alkalinity. So you got to somehow counterbalance that alkalinity that's brought with these fluids. So there's not a perfect model here, but there are some definitely some options. The main thing I want to show here is that these incredible layered materials, they're linear, that are going across here in this sedimentary deposit. We call this the Burns Formation. We named this after one of our famous mineralogists from a number of years ago that was really interested in these iron sulfides potentially being on the surface of Mars. But it's mainly sulfate, a lot of hematite. 20% of this is iron oxide, so that's quite a bit of it. Silica, 20% is igneous materials, so minerals like feldspars. The olivine and pyroxenes have probably been destroyed by the acidic processes. But what we did see here were numerous exposures of sedimentary materials. Here you see this linear feature again. We think this linear striata is probably due to what we call an active sand sheet. This was produced by wind. We also see these really large angular cross beds that were probably dunes. And then we examined a large impact crater, Endeavor Crater, and we found a considerable amount of impact material. Here's one of our latest and greatest on the stratigraphy of the Burns Formation, or this depositional environment in Meridiani. The lower portion of this is mainly large angular cross beds. These are due to eolian dunes, wind-blown materials, and then these really active materials that are being blown across the surface by the wind, causing these eolian sand sheets. But at the very tops of these materials, we see the interaction of water. And the reason we think that is we see what are called festoon cross lamina. These are these wavy boundary things you see in these images that suggest that water has reworked these materials near the surface. So this was probably some kind of an interplaya dune material. Okay, I'm going to leave the Mars exploration rovers, and I'm now going to jump to the northern latitude on Mars. This is the landing site for the Phoenix lander. We landed about 68 degrees north, so we were quite a ways north. And here is the lander, the gases that might be trapped here in this materials. And I'll talk a little bit more about that. But also to convince that we would encounter a layer of water about 15 to 20 centimeters under the surface of the lander. And here's one of the instruments called the Wet Chemistry Lab. Being a soil chemist, this was incredible. Here we have a instrument that we add soil, we mix in water, and we measure the chemistry of that solution. What was the pH? What was the redox conditions? What were the cations? What were the anions? So we could actually measure what was going in the solution. Of course, this is crucial for understanding if this particular solution would be instrumental in keeping a microbe alive for habitability. And the other major instrument that I actually helped build and did a lot of the testing on this particular unit is the thermal evolved gas analyzer. Here we introduce soil material into an oven. We heat that oven up. And then as it is heating up, we sniff those gases with a magnetic sector mass spectrometer. So we could actually detect the gases that were coming off. And I love this analogy. I had the opportunity to spend 2 field seasons in the Antarctic dry valleys doing analog research for this particular mission on Mars. And here you can see these analogs on the left, the expansion and contraction of subsurface ice. And this is the area on the right of what we see on Mars, suggesting a very similar process in place. And we landed, and we didn't even need to use the instruments. The first thing we did with the camera on the end of our arm, we looked under the surface of the on the surface under the spacecraft to just see what if there's any damage to the spacecraft. And lo and behold, the thrusters had blown the dust and material off of our layer of ice. So right there was the ice. And of course, leak out. Now this is looking off to the distance at the surface, and you can see this polygonal pattern that's out here, again suggesting this ice subsurface. We were able to dig down to the ice layer. This is actually hard as a rock because this is the ice. We then developed a rasp. I actually developed this rasp material itself and tested it in our labs at Johnson Space Center and to see how this would work as far as delivering this material subsurface to our instruments. And what we found was some really, I think, in all the research I've done on all of the landers and orbiters, the data that's coming out of the field discoveries on Mars is pretty amazing, but the Phoenix spacecraft has told us a lot. One thing was that we were forming what we think in situ carbonates, probably around thin films of material. So liquid water was interacting with the surface materials. And the reason we think that is we saw a pH under Mars atmospheric conditions that would suggest that we were in equilibrium with carbonates. On Earth, it's 8.3. Under the conditions on Mars, it's about 7.7. And then we looked at the evolved gases, and the CO2 that was coming off, particularly the higher temperature CO2, was at temperatures you would expect for the thermal decomposition of calcium carbonate. But probably the biggest discovery that has kind of revolutionized the way we look at Mars was this particular measurement. This is when we added the soil material, and we were supposed to look for nitrate, and the sensor went nuts. And there's not enough nitrate you can put into this system for what's called the Hofmeister series ion selective electrode to cause this response. The only thing that could do this was perchlorate. So we discovered that here on Mars, we're seeing a whole lot of perchlorate. And I'll just mention on this one that the amount of perchlorate we saw was around 0.5 weight percent. So there's probably 1 to 2% perchlorate salts in these materials. Now, we didn't get bulk mineralogy, but we sure proved a lot of things. That there was subsurface ice, there were perchlorates, there were carbonates that we think were forming in what I would call pedogenic. Okay, so I'm going to jump over again to the other lander. This is Gale Crater. This is where Curiosity landed. You can see again that we landed at this area, this dichotomy on Mars, where you have the highlands to the south and the lowlands to the north. And here is a really interesting thing about this one, crater, and on this dichotomy is it has a very large mound of sediments in the interior of it. So one of the hypotheses that we have is that water from the highlands to the south subsurface moves its way to this dichotomy, and water then upwells in this area. And here's where we think water was probably more concentrated over time on Mars than other places, as far as being able to provide enough water for longevity for potential habitable areas. And Curiosity was primarily to look for the biological, potential biological activity or habitability that could have been supported here in the past. So we're mainly looking at past climatic conditions, but also we are looking at the current climate on Mars, as well as radiation hazards. So as I mentioned, Mount Shar, there's a large mound of sediments in the middle. We termed that or dubbed that Mount Sharp. This Mount Sharp, we think, is nothing more than just layers of rock and sediments. And this thing is over 5 kilometers. Standing in the United States over at Seattle, looking off towards Mount Rainier, you're seeing about 14,000. This is equivalent to about 16,000 feet in elevation. So it's a significantly higher than that difference that we see from Mount Rainier. And if those of you that have been to Seattle and seen this, it's quite spectacular. Now we came here because we saw these interesting layers of material from orbit, we saw what appeared to be, again, hematite bearing materials. And then the one that really drove us here are these clay mineral bearing materials. We saw signatures of these hydroxyls on our Mars, suggesting that these were some type of phytosilicate clay mineral. And in particular, the one that we are most interested in, or think that it was from orbit, was the phytosilicate mineral group called smectite. And I'll talk a little more about that. But then as we go up the slopes of Mount Sharp, we see this drying out period on Mars, and the beds of sulfate bearing material. And I'll show that next on this slide. I love this slide. We see some Aeolian dunes dance, ported the rover all across the Murray Formation, the Hematite Ridge, the clay mineral material I talked about. And today we are right up here at the base of Mount Sharp. And towards the end of this, I will show you a spectacular view of the sulfate units that we are currently looking at. But here's what we see from the ground. And of course, you can just see tons of layers going up the sides of Mount Sharp. Incredibly spectacular view from the surface. So first of all, I'm going to talk about an area that we investigated called Yellowknife Bay. This is probably the key to the early portions of the mission. You can see the burn marks on the left here of our thrusters as we landed. And then you see the rover tracks, and we made way over to this low. Now, when we landed, we thought, well, you know, there's a low off to the east about half a kilometer. That would be an area from orbit. It looks like it was solid bedrock that water might have ponded or might have been deposited materials. So we made tracks over here to this area called Yellowknife. What we call a sand shadow, or just an eolian deposit. It's fairly ancient, meaning it may be 20, 30, 40,000 years old that this material's been deposited here and been building, and maybe been some of the materials being removed. But we mainly looked at this to test our instruments. But I look at this as a golden opportunity to look at the chemistry and mineralogy of the surface materials. And here are close up with our geologic hand lens called the Molly instrument. You can see these really fine grained materials here, and the coarser grained sand sized materials. So gave us a whole lot more perspective of the materials that were being deposited around the surface of Mars through aeolian activity. Now, I am a mineralogist by training, and I have seen a lot of images from the surface of Mars, but this image may be my favorite image of all time returned from Mars, and that is because it gave us the first definitive mineralogy from the surface. This is a ring pattern of diffracted X-rays off of the atomic planes of the minerals themselves by an X-ray diffractometer. So here you can see those material. We knew it was basaltic in nature, so we proved that yes, it was basalt. Feldspar, olivine, pyroxene, magnetite, all those great things you would see in a basaltic material that had just been erupted from a volcano. However, we saw a lot of altered materials in this soil windblown material as well. Sulfates, the calcium sulfates and hydrite basanite, again, iron oxides, hematite and ilmenite, but a large fraction of this material did not coherently diffract the X-rays, and this material was amorphous. And we also had the capability to look at the evolved gas analysis, much like the TIGA instrument on Phoenix. We heat a sample up, drive off the gases, and sniff them throughout the entire temperature that we're heating these up. And some of the big ones that came out of this is there's quite a bit of water. The surface materials have about 2 weight% water. That was a major discovery. But they also were evolved a considerable amount of oxygen around 350 to 400 degrees C, as well as these chlorinated hydrocarbons like CH3Cl. And they came off at about the same time the oxygen did. And here we think we're seeing the thermal decomposition of these perchlorate salts again. And we've done a lot of work here at JSC to show that almost certainly we are looking at perchlorate and chlorate. The two of them together could form by atmospheric processes is one way we think it did form. And so we anticipate that both perchlorate and chlorate are present on the surface of Mars. Now, the perchlorate and chlorate are inferred, but this evolved oxygen, the timing of the chlorinated hydrocarbon release, and of course the Phoenix results, all lead to what I think are organic material that when you heat up this perchlorate in an oven, if you're looking for organic material, the perchlorate thermally decomposes about 350 degrees C, and that is about the same temperature you would expect to see organic materials start to decompose as well. And instead of getting nice fragments of organics, a lot of times all we see is a lot of CO2 being evolved because it is combusting the organic molecules. Here's an image. We're heading down into Yellowknife Bay, this low where we think that water once ponded. And here we have two drill sites that we first drilled, John Klein and Cumberland, into an area we call the sheepbed mudstone. This is a fine grade mudstone. And here is our drill hole of John Klein. Unique thing here about this is you can see this fracture that's running down into the borehole itself, and it's lighter toned. We think this is calcium sulfate that has been remobilized in a fracture or a crack within this material. And here you can see these black little blebs down into this. These are shots from our ChemCam instrument. It's a laser that blasts the surfaces of materials, and in this case down this borehole, evolving gases that are plasmas that are then looked at by the spectrometers on the eyes of the rover and giving us information about the chemistry of those plasmas. And again, a beautiful image from Mars, the X-ray diffraction, diffraction rings for this material. And the unique thing here is this high amount of scatter down in this area that is due to phyllosilicates. So here we found our clay mineral. And what was unique is that we found a lot of it. There was about 22% clay mineral in this. And we think that it was a smectite, probably a collapsed smectite due to the nature of the surface of Mars, meaning being very desiccated. And we also were able to hypothesize that this material was almost certainly trioctahedral, which is important for its formation, whether it's dioctahedral or trioctahedral, gives you information about how this smectite formed. And again, a large amount of amorphous material. Now, I'm not going to get a lot of detail here, but we had a sensitive enough instrument on Mars to look at the differences in some of the D spacings. These are the D spacing, the spacings between the atomic planes within the phyllosilicate itself, that we could differentiate a trioctahedral from a dioctahedral. In this case, we think this was a trioctahedral. This probably formed under more heat. Heat could have been involved in this, maybe pressure. We think that this material probably formed a little bit more under hydrothermal conditions, which if you're looking for life, this would be a great place to potentially do that. And here are the evolved gas analysis from these two samples. Here we see two unique water peaks. This water at the lower end is probably just water being released from absorbed or inside the clay mineral itself. Their water will be inside the clay inner layers, but we also see a very high release of water. And this water is due to the thermal decomposition of the clay mineral for trioctahedral, ones that have magnesium and in their hydroxyl layer or the octahedral layer, and that is water being evolved by the thermal decomposition. So between the X-ray diffraction and the thermal evolved gas analysis, we're pretty certain that this is trioctahedral smectite. Again, we saw the release of oxygen and these chlorinated hydrocarbons, suggesting that there was also perchlorate that was in the sedimentary record itself, the rock bed itself. There's a lot of debate even amongst the team members on whether this perchlorate is recent or whether this perchlorate is ancient, because these sediments were laid down about 3 to 3.5 billion years ago. Was it at that time incorporated into the rock, or did it come in afterwards? So what we found was right off the bat in the mission, what we think is an ancient habitable environment. We got this really fine-grained rock that suggested that water was flowing into this area and depositing these materials. The mineralogy with these smectites forming suggested it wasn't too acidic. It was probably just somewhere around neutral, maybe slightly alkaline. But a key here was that all the ingredients for life are present. So the evolved gas analysis and our chemistry experiments on board the rover all suggested we had the key things of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the chomps. So that is a key. Then we had various oxidation states. We had reduced iron, we had oxidized iron, and of course you need electron transfer for metabolic metabolism, and so this could have been an energy source for primitive organisms. And here's an image. We left that area and started tracking the rover tracks just as we've gone through a sand dune. And here shows our trek over to the base of Mount Sharp, and the red arrow you see is where we are today. And I'm not going to be able to go into a lot of detail here, so the next few slides will be a flurry of what we saw here. We've drilled 30 holes on Mars. We've just drilled our last one this past 2 weeks, and we're analyzing that sample now. The unique thing here is look at the colors. Now, lighting and how you take these as far as the angle of light does make a difference, but those had more iron oxides than the gray material. So the color really does tell you a story here about some of the oxidation nature of the material as they were being emplaced and diagenetically altered over time. Again, we saw a very different mineralogy as we've gone up this trek. We saw clay minerals at the bottom part. We saw areas where there were higher silica and an area that was near the bottom, but during our trek up the hill. And then we're back into an area where we're seeing a lot of clay minerals and a lot of sulfates and variable amounts of iron oxide. And that's important because the iron oxide pretty much tells you where the areas that you might expect to be more resistant to weathering. And we did see that in the Vera Rubin Ridge area, which is that ridge of hematite iron oxide that we see from orbit. The materials we saw at the base and all the way up through, we've seen these really fine grade mudstones, these clay minerals that are all we interpret as being lacustrine in nature. We've encountered conglomerates that look like they were emplaced there by high activity of water, outflow channels of rivers, for example. And then we see sandstones that are all deltaic, and then these really fine grained materials as we're going up the stratigraphic column here, suggesting, again, lacustrine deposits. This is one of the views about midway on the trek. These are these sandstones that are all dipping towards Mount Sharp. We think that those are cascading down into the lake bottom material, and these are deltaic in nature. And then here's some of these really fine grain materials that we think are lacustrine, were deposited by the bottom of lakes. And this just gives you a cartoon by one of our scientists on the team, Chris Fetto, who shows the crater and these materials washing down in. Then you see these receding and expansion of the material for prograding fluvial systems, these deltaic deposits, and these really fine grained mudstones at the bottom of the lake. Now, the key question for habitability, how long was the water there? Was it there long enough to potentially sustain any microbial activity? And the other thing that's key is that we hypothesized that the lake was shallow at times and it was deeper at times. When it was shallow, it was more oxidized. We see evidence for more oxidized materials like iron oxide, hematite. And then when it was deeper, more reduced, we see things like magnetite and silica. So this is suggesting some chemical redox stratigraphy within the lake itself. So this stratified lake could have been a key place for life. Question is, how long? And I'm showing this one because this was one result I thought was incredibly exciting from the mission. We were able to date the jarosite in one of our samples using potassium argon age dating using our evolved gas analyzer, the SAM instrument. And what we found is that these materials, the jarosite, formed about 2 billion years ago. The sediments were deposited 3 to 3.5 billion years ago. So here we are looking at the possibility of the interaction of water with these sediments for over 1 billion years. This to me was incredibly exciting because this was the possibility that we might have an environment that could sustain microbial activity. Now, I'm not going to get into a lot of organics. I told Dimitra that I would be happy to put you all in touch with our experts on the team with that. But we did see methane in our daytime measurements in the atmosphere. There's a lot of argument over where that methane comes from. It could be inorganic, just geologic nature, where you have olivine and water working during what was called serpentinization reactions. You have the outgassing of things like methane, or you cannot rule out the possibility that there could have been microbes, and there still are microbes that are involved in this generation of the methane. So we'll continue to debate that. We have evidence for organics. With the perchlorate in our samples, it's pretty tough to get good old organic fragments, but we did see a few and a lot of chlorinated carbon, and one of those was chlorobenzene. We attribute that as Martian organics combining with Martian chlorine. And then more recently, we were looking at material where we saw higher molecular weight organics, and they were all associated with sulfur. So these are sulfur-containing organic compounds, and we recommended or suggested or hypothesized that these was due to the sulfurization of the organic material that helped preserve it over this period of time. These publications, and I hope that we put you all in touch with some of our experts. And I love this one. Image. This is this mudstone, what we call the Murrius Mudstone, and these ancient Aeolian beds over the top of it. They are what we call unconformably overlying this material, which means that a lot of material has been stripped off here, and then this was put down on top of this old mudstone. We don't know how long after that was stripped off this was put down, but this is a really unique contact that we've done quite a bit of work on Mars. Okay, so I'm going to wrap it up here and just tell you that we are at the base of Mount Sharp right now, looking at what we call Mount Marcoux. This is a 7-meter high outcrop of what we think is the sulfate, but basal portion of the sulfate unit. So we're now going from the clay mineral unit, which is down here at the bottom, transitioning up into this sulfate unit. So this, stay tuned. This is a new, exciting time in the mission. And with that, I'm just going to stop here. These are some of the major scientific findings from the Curiosity rover. And I'll open up to any questions for the next 10 that we have.
All right, great. Thanks a lot, Doug. Yeah, we are back on Earth now. So yeah, please raise your hand or put your question in the chat box. So first question is by Daniel. Go ahead, I have unmuted you. Daniel, you can, yeah.
Yes, can you hear me?
Yep, go ahead.
Okay, hi, thank you for the presentation. Really exciting stuff. I'm from, my name is Daniel Moraitis. I'm from University of Sharjah. I'm the last 2 years here, and before that I was in Oman. We started with some students working on trying to make artificial soil similar to the soil that exists on Mars. And I know that already some universities, they have succeeded on producing some artificial soil. But maybe you have said that, and sorry if I'm repeating that, but my question is, because we were based on one of the publications from the Curiosity that came out in 2014, what type of clay minerals we know, if we know, that exist on, I mean, when I say clay minerals, I'm talking about secondary minerals, not the size, but the type of micas or whatever exist on the planet. Do you have any information on that?
Yeah, I think the question was what types of clay minerals, if you're going to make a simulant, would you use? One of the key problems with trying to recreate that causes clays to collapse and lose its water. So that's one of the key things that we will probably never be able to really get under let's say a lab environment unless you do it in a Mars chamber. And so it's going to be a difficult thing to do. But we have a lot of information about the clay minerals. We actually, my colleagues here at the Johnson Space Center and I developed a Mars simulant based upon a kind of a common material that we have seen here in Gale Crater. And that publication came out last year. You might look at that. And as far as the clay minerals, again, more information about that, I would suggest the Bannerman and the Bristow papers that we've published. And we just think we're about ready to publish another paper in Science that will talk more about this, what we call trioctahedral to dioctahedral transformation. So that might help you, give you more information on the clay minerals as well.
Okay.
It's a fun task. I applaud you, Miguel, and your students for looking at the ways of making it on the surface of Mars.
Doug,
yeah. It's for us, you know, here in UAE and in Oman. There are all these ophiolites, and you have quite of material that you might select and then, you know, do some mixers and try to produce at least for fun for the students and try to see what's the best way to mix materials and develop kind of techniques of you know, approaching as much as possible what is already published as Martian soil, and then from that to use it, you know, for further experiments. That's our target. But thank you. I will follow the publications that you mentioned.
And just one other thing real quick. You know, I work with folks all across the planet on doing just exactly what you're talking about, materials that are local. Can we make Mars simulants out of them? Most recently, I worked with some colleagues at the Agricultural University in Greece, where they've took materials from Santorini, and we looked at those as analog materials for Mars surface materials. So it's always good. Be a great student project. Work on looking how that could be incorporated into our knowledge of Mars, and a lot of times you can get a publication out of that. That's the cool thing.
Cool. Yeah, Srini, go ahead.
Yeah, Doug, I'm very pleasantly surprised and impressed by how much geochemistry one knows about Mars. I have two very maybe shallow questions about this recent paper in Nature Geosciences or whatever that said that most of the water on Mars still remains on Mars. Stored in minerals or something like that. Do you have an opinion on that?
Yeah, you know, I've listened to the folks from Caltech's presentation and read their paper and looked at it a couple times. Yeah. And It's a valid point that there is no doubt quite a bit of water that has been incorporated in the crustal materials during the reprocessing, and the question is how thick and how deep is it and all that, and they've gone into the calculations of what that would be. But at the same time, we look at the DDH ratios from the phyllosilicates from that time era, and we did that with the SAM instrument. Mahaffey et al. We looked at DDH ratios, looking at those isotopic compositions. We look at the MAVEN data sets. We'll look at see what you all come up with, and I think there's still a lot of evidence that there's a lot of atmospheric loss. Now, was the water budget much greater then, or than it is now? Than we thought it was? That'll be a debate. But I'm still kind of tossed between atmospheric loss of a lot of the water early in the planet versus this tied up somewhere crustally now. I think we got work to do on it yet.
Yeah, I think that's a very interesting topic. But about the volcanic activity, volcanic material that you mentioned pretty early in your talk, do they bear any resemblance to volcanic material on the Earth?
Yeah, it's basalt. So basaltic eruptions on Earth are, I think, incredibly similar to on Mars. There are some really unique differences. Mars has more iron crustally than, or probably in the mantle when these things are going on, than Earth, and it has less aluminum. And it's also probably higher magmatic sulfur. It's kind of interesting you asked that. I had a big powwow with some of our leading scientists here that are igneous petrologists looking at this particular question, trying to answer the fact about sulfur. What about all this sulfur we see at the surface? How can we explain that? And what it does is it points to more sulfur in the crustal materials, more sulfur in the magma. So the outgassing of that magma, and that's why we see sulfur, I think, all over the planet like we do. It's just there are a few things that are slightly different, uniquely different than on Earth. But basically, if I were to go to Mauna Kea volcano in Hawaii, and I have done that a number of times. In fact, I've spent many field seasons studying the volcanism on Mauna Kea. It is a dead ringer for a lot of the mineralogy, a lot of the chemistry. Just a few things that we different is the iron state, higher iron on Mars, and the aluminum state, lower aluminum content on Mars. But other than that, it's just like a lot of the terrestrial
how much bigger is
the
iron content? How much bigger is the iron content?
Yeah, so the iron content on Mars is about 18 to 20 weight percent FeO. On Earth, you might see half that in these mafic, ultramafic, and it depends on whether it's, it's all dependent on the differentiation as it is coming, the magmas are coming up with you, and the temperatures and a bunch of other factors on how you separate out the iron, the manganese, and magnesium and other things. So it does vary. You end up with what are called, in iron and magnesium, but you're looking at about double, for as a general arm waving number.
Yeah, thank you.
Yeah, any other questions? Please raise your hand, type it. Yeah, we have another question. Yeah, Vladimir. Go ahead, Vladimir.
Yes, hello. Thanks for great talk. So I have a couple of questions. So do you see any spatial distributions of bar rates on Mars in different places? And the second question about the same thing, the spatial distribution of the nitrogen 14 to nitrogen 15 ratio, the isotope of nitrogen. So thank you.
Yeah. I'm not a great isotope geochemist, but we do see some. I think, from our orbiters is going to be the best we can do on those, because we've only really measured some of these isotopes at a spot or two on Mars. So we have a paper. It's by Jen Stearns that talks about the nitrogen isotopes on Mars. I would direct you to that paper if you haven't seen that. That'll give you more information about what we know and don't know. We don't know a lot about the isotopic nature of nitrogen on Mars, but at least from a rover's perspective, that's about as good as I can send to you. Now, I didn't quite hear the material on the first question. It was spatial distribution of what was it?
Borates on boron. On borates on Mars.
Borates. Oh,
Yeah.
borates. Well, yeah. So, you know, that one's kind of a funny one. I have not followed too much of our borate story, our boron story, but with our ChemCam instrument, this is this laser ablation spectrometer that can blast the surface with a couple different lasers, wavelengths, look at the plasma. We see boron, and there's a paper out by one of our scientists on the team at Los Alamos that talks a bit about that. If you haven't seen that, you might look at that. But as far as the spatial distribution, that would be the best one to look at. And yes, the answer is yes, we do see differences in boron across the trek of the rover. And so there are areas that are higher boron than others. And most of those are associated with vein material, which suggests that these materials are being remobilized by aqueous fluids and being moving through the sedimentary record and being precipitated probably as a last gasp of water in some of these materials. So I would expect that that paper would probably help with that question quite a bit if you want to look at that. It's Patrick Gazda is the name of the lead author on that paper.
Thank you.
All right, any other questions? If not, then let us thank our speaker. Thanks again, Doug. Thanks so much. This was very exciting. And there is so much that we can learn from this. We are actually building a Mars lab here where we use simulants, and we are trying to study the interaction of UV with perchlorates and organics. And I mentioned this briefly with you. And yeah, so this is really exciting, and thanks so much. And
well, I enjoyed it. Thank you for the time. And if I can be of any help, let me know. I'll be happy to help where I can.
All right. Thanks so much.
All right.
All right. See you all next week. Bye-bye.
Yeah.